Is Radu Ignat from Toulouse.
Thank you very much. And thanks the organizers for the nice invitations. It's really nice to be back in Cambridge after 6 years since the previous semester on liquid crystals. So I would like to present today some issues about proving symmetry in phase transition models where there is constraint on the divergence of the order parameter. So in this conference we saw many types of microstructures that appear when you do the transition between two phases. So let's say that I'm interested in the opposite situation where you have one-dimensional symmetry when you do the transition between two phases. So this means that the order parameter will depend just on one variable, and it stays constant in the orthogonal directions to that preferred direction. So the question is, how can you prove symmetry? So how can you prove that one-dimensional configuration is optimal in a variational model? So in general, what you do is you try to do a matching between an upper bound, that in this case it's easy because you will just plug in the 1D configuration, and the lower bound. And in this situation, the lower bound is very difficult to get because in some sense you want to prove that for the full admissible configurations, the energy will stay above the energy of this 1D structure. So the aim of my talk is to highlight a method that is quite known in calculus of variation, which is the calibration method, or sometimes called also entropy method, due to the relation with the scalar conservation law coming from this divergence constraint. And so this calibration method is consists in proving this lower bound by introducing a new energy which is much simpler to analyze, but which still matches the upper bound, okay? And this energy uses this notion of calibration. Okay, so in my talk, first I will motivate these kind of questions by giving some models from material sciences, and then we will go to results. So all this work is done with my former student Antonin Monteil, who's now postdoc in Belgium. So let me start with a first model that comes from smectic A liquid crystals. So in the smectic A phase, you expect that the molecules are arranged on layers. So consider that these layers are level sets of a function phi, and then the director is given by the unit normal to these sets, okay? So the director, you could see it as grad phi over modulus of grad phi. And then let's say in the easiest situation where you apply the Ozen-Frank theory for equal constant elastic constants, then you would like to solve to minimize this Dirichlet energy. So like this you will have a link with the harmonic map problem. But there is a problem. This vector field is ill-posed, right? Imagine that on the boundary, you want that the boundary is a level set of your function phi. So let's say phi is 0. So of course there the normals, so your n will be the normal to the boundary, so you will have this hedgehog boundary condition. So therefore you expect that inside you will have points where the gradient is 0. So then what is the meaning of this term? So therefore, there are several ways to relax the problem, and one way to relax it was introduced, in fact, by two mathematicians, Aviles and Giga, who said, okay, let's forget about this denominator, and let's take the normal, which is not normalized. So let's speak just on gradient fields, and let's put a penalization that will constrain that when epsilon goes to 0, v will get of modulus 1. So right, v is a gradient field, and you take this let's say Mexican hat potential that has the zeros where modulus v is 1. So since we are in a 2D problem, that's the unit circle. So indeed, okay, so this is easy to prove that for fixed epsilon you have a minimizer. So this problem, it's easy. And then you expect that when epsilon goes to 0, you will have some relation with this, let's say, ill-posed problem. So let me say that there are also some other relaxed models that for smectic liquid crystals, like the paper of Wayne and E, and also the nice paper of John with John Ball and Bedford, where they also speak a bit, they introduce a model for the Q-tensor theory. Okay, so right, so the first question is, do you expect that these minimizers converge, right? So at epsilon strictly positive, and what's the information that you get when epsilon is 0? So this is this limit is very complicated because this model is highly nonlinear, and you could expect a lot of oscillations coming there, so that the modulus is lost in the limit, right? So, but okay. So the answer is, in fact, that you have the compactness, and so you can prove that the minimizers of that functional will converge to a vector field in, let's say, in an enough powerful topology, L1 almost everywhere, where you could say that, okay, of course the fact that it's a gradient field will go to the limit also, but you can say that at the limit you are modulus 1. So this v is exactly the n that we started, right? Because the n was this divided by the modulus, but that's 1, okay? So the question is, what's the structure? What's the structure of the minimizer? So already from the limit problem, you could say, okay, the limit equation is this aconal equation. So in general, the typical solution that you expect is the distance function, let's say to the boundary, if you know that phi is 0. So in my title, I say that I want to prove symmetry for the divergence constraint. So since we are in 2D, being a gradient field or asking to be divergence-free is the same thing, because you just do a rotation by pi over 2. So already in these pictures, but in the divergence-free configuration, you see that in a disk, well, you expect to have the hedgehog turned by pi over 2, so you have this kind of vortex appearing here. And if you are in a rectangle, you could see what is sometimes called the Landau state, this kind of shape, where you see that, so the normals, right? I mean, U is the normal. So they cross through these singularities, where U will change the direction. And now is the question, so I'm interested in the structure of the minimizer. So now our question comes out. Let's suppose that we want to see what's happening between these two states. So this direction and this direction. So imagine that here you will place a strip and you make a zoom when epsilon is strictly positive. And you can ask, if you minimize the Aviles-Giga energy, can you prove that the 1D structure is optimal? Okay? So let me tell you that at the end of the story, we will prove that this is true. Okay, at least for this potential. Okay, another motivation. So this makes the connection with the talk of Cyril. So these motivations come from thin ferromagnetic films. So let's say that we want to model a small magnet. Okay, so that's a region in R3, and inside the magnet, well, you have the magnetic moments that can be seen as a vector field that is normalized, so it will stay on the sphere. Okay, and as it was said before, so these magnetic moments will induce a magnetic field that lives all over, so which is the stray field. And let's consider that we place in a regime where this stray field is strongly penalized. So you impose divergence-free. So therefore, you expect to have this kind of closed field configuration. Okay, and then the micromagnetic energy in the absence of applied magnetic fields can be given again by this kinetic energy and a potential energy. And this potential energy is the anisotropy, which is a positive quantity, and the zeros will be the preferred directions of the magnetization. So for simplicity, imagine that you penalize the vertical component, so you prefer to be in plane. Okay, so what do you expect in general? You expect that there are these kind of regions that are created, they are called magnetic domains, where the magnetization stays almost constant. Okay, and what you see here, of course, it's what you see when if you imagine that you have a 1 epsilon there, epsilon is 0, right? So these are sharp interfaces that, of course, will be infinite energy for this. And so you see these interfaces that represent the walls. And again, the question is, when you zoom over here, what do you see? Do you see a transition between these two directions that is one-dimensional, or you could see some microstructure? Well, of course, you can see both. So, so in the situation where W is exactly M3 squared, so in fact, this is quite similar with the Aviles-Giga, because since we are working with values in S2, M3 squared is nothing but 1 minus the in-plane component to the squared, right? And so that's the 2D model. And so as I said, so if you imagine that, for example, you are in a strip here, then in that situation you can prove that the one-dimensional model, the one-dimensional configuration is optimal. So here is, for example, you want to go from this direction to this direction. Then what you do is, so this is the let's say the tangential component here. So from here to here, you will do like this, right? So in fact, what's happening is that imposing that you are divergence free, it means that the normal component on the wall should be the same. So when you are 1D, it means that okay, in this situation, the normal is 0, right? So you need to stay on this circle. Okay, so that's the situation here. But of course, in some other situation, you expect that there is a microstructure appearing here. So see, when you will go from here to here, you will see this kind of cross-tie configurations appearing here. So clearly, the 1D is not anymore optimal. Okay, so what's the model that we study? So, sorry. So what's the model that we study? So we place ourselves, so we can do in any dimension. So we place ourselves in a strip. And so you are periodic. Let's say that you are periodic in the wall directions, and you take a vector field that is Rn. So of course we don't do the micromagnetic model where we ask to be modulus 1, but that is sometimes penalized here. Okay. And we ask that these n-dimensional vector fields are divergence-free, and we want to minimize this kind of energy, okay? Where W is always a positive potential, and of course we want to see the transition between two wells, so two zeros, right? So the question is a minimizer of this problem 1D. So of course already I put here the mean. This is not a trivial problem, that since you are in an infinite domain and the energy is a translation invariant, of course you could have this kind of loss of compactness, so you could lose the boundary condition that you impose at infinity. So this is not trivial, but of course, so we also studied this, but I won't go into this in this talk. But first of all, let's say, what do we mean by this boundary condition? So okay. Let's say that we take a configuration, so this n-dimensional field that is divergence-free, and let's say that is finite energy. So the gradient is in L2. Then what we do is that we will consider the average. So the average in the wall. So on that section that is the n-1 torus. Okay. So, of course, since this is square integrable, then of course the average is the same, but since you are in 1D, this means that this function is continuous, okay? And now, since you are divergence-free, then if you consider here the first component, that will be constant. Why? Because if you do the derivative in the first component, then the derivative of the first component is nothing but minus the divergence in the other components. But since you are in this periodic setting, that's 0, right? So you get that this is 0. So this means that you are obliged that those wells will have the same normal components. So this is what I explained before, but that's a proof. Okay. So our boundary condition is that we impose that this continuous function has these two limits, u plus and u minus, which are the two zeros of W. So for example, in this situation, right? So you want to go make the connection from here to here, and for example, the average is obliged to stay within to make the transition within this line. Okay, so now if you are coming more from a PDE community, then you say, okay, what's the PDE out of that? So when you write the Euler-Lagrange equation, of course you have the Laplacian, then you have the gradient of the potential, and then you have this pressure appearing due to this divergence constraint. So that's a highly complicated system to analyze, and of course one would like to prove this one-dimensional symmetry, at least for minimal solutions, right? Because there is an energy out of that. So right when you work with systems of elliptic PDEs, in general you don't have even the maximal principle. So then the question, you say, okay, what's happening if you simplify the problem and you take the scalar version? Well, now the scalar version is nothing that what is called the de Giorgi conjecture for minimal surfaces. So that was a problem that was highly studied in the last 30 years, and it was solved almost solved 10 years ago. So which consists in studying this, in proving one-dimensional symmetry, at least in small dimensions, for this problem. So let me state this this conjecture in terms of PDEs. So here you consider this let's say scalar double well potential, because it's a scalar problem, and so you will consider now a solution to this problem, right? So Laplacian equal with the gradient, where you ask that the solution stays monotone in one direction, and that it will make a transition layer between the two stable zeros of W. Then the conjecture is that at least in small dimensions, all the level sets are hyperplane. So this means that your solution is one-dimensional, meaning that you have a profile that depends just on the direction, the normal directions to those hyperplanes. Okay, so now you say, okay, so what's the relation with the minimal surfaces? So let's say that this is a transition layer that happens on an infinite scale, but now if you rescale, you want to make the things on a epsilon small scale, then of course you will rescale your function, so you will have an epsilon coming here, 1 over epsilon coming here, so that kind of modica mortola, and when you make epsilon goes to 0, then you will get that this is nothing but the perimeter energy. And you always expect, as it was said also yesterday, that when you minimize perimeter or area for interfaces under some constraint on volume or some other things, then you expect to have minimal surfaces appearing. So therefore, the minimizers of this will converge to something where the level sets will be should be minimal hypersurfaces. So again, you can put the question, okay, what other W you can put here in order that that this is true. So as I said, this problem was solved. So first of all, in dimension 2, by modica mortola, okay, they didn't solve completely the problem, but then it was Gusub and Gui that proved it using some Liouville type theorems and the monotonicity formulas. Then Ambrosio and Cabret succeeded to prove also in dimension 3, and then Ovidiu Savin came with a different proof by using regularity theory for the level sets, and proved that this is true up to dimension 8, provided that you add this pointwise convergence at infinity. And then, so that was like 2008. and then Del Pino, Kowalczyk, and Wey prove that in dimension 9 you can cook up these solutions where, for example, a level set will not be a hyperplane anymore, but will be this what is called the Simon cone, which is a microstructure. And now, in the last 10 years, there is a lot of literature studying this problem, but for vectorial setting. So there, the order parameter will have several components. So this comes in general for in phase separation models, like you can consider Bose-Einstein with two spins, and they try to answer under which conditions you still have the one-dimensional symmetry. Okay, so let's go back to our problem and see what's happening. So let me recall. So here we are working with the n-dimensional fields. So it's the same dimension in the target and in the definition domain. This energy we impose divergence-free, and this boundary condition through the average. Okay, and the question is, for which potentials do we expect that that a minimizer is 1D? So yes.
So before we were looking at the Euler-Lagrange equation.
Yes.
So no need for finite energy concerns. Here you're formulating.
Exactly. So yeah, that's a good point. So since we will work with energy methods, I would like to have my energy finite. So that's why in the De Giorgi conjecture, they don't care about. They use PD methods. So you can be in every Rn. But now if I'm in a strip, so a one-dimensional transition has finite energy. So if I put it in a strip, it will stay finite energy. So it's okay. Okay, so as I said, the existence of a minimizer is non-trivial. So we studied in our paper, but I won't speak here, and I will go directly to the proof. So as I said, proving this one-dimensional symmetry means that first you need to compute the upper bound and then to match it with the lower bound. So now you are so the upper bound will be quick. Okay. So first, okay, a model in order to see the difference between asking divergence constraint and not asking divergence constraint. So let's go back to the Aviles-Giga model. So you consider this potential. So the zeros are the circle, and you want to make the transition between these two wells that that they have the same projection into the direction x1. So already Aviles and Giga and Gin and Kohn prove that the one-dimensional profile is a global minimizer. Okay, but of course we are interested in something more difficult. Can you prove that every global minimizer is 1D? So okay, so of course this 1D, as I will explain, it's easy because in 1D it's nothing but an OD coming here. But so at the end of the day, you will see that the 1D is the unique global minimizer. But what is interesting, because we want to know what kind of shape you can put in W. So Gin and Kohn said, okay, but if you make this isotropic circle, you make anisotropic, so you make like an ellipse, then the 1D profile is no longer a global minimizer. So when this delta appearing here is very small, then you can cook up a microstructure. Okay, so the shape of W is really important. And now let me stress why there is a phenomenological difference working with the divergence constraint or without. So a 1D configuration, as I said, should stay in this line, right? Due to the divergence constraint. But now, if you forget about this, of course, you can make a connection through the zeros of W. So this energy is 0. Of course, you pay something here, but if you make it on an infinite scale, you can go to 0. But of course, you can never have a configuration that is constant, right? So without the divergence, the minimizer do not exist. Okay, so like this, you see why there is it's important when you want to prove this symmetry, the divergence constraint. Okay, so now the upper bound. So let's we need theorems that will tell us for which kind of W the one-dimensional transition exists. So let's go do first in dimension 2 because that's easy. So one-dimensional transitions is nothing but working, for example, with the average. Yeah. So the only condition that you need to impose in order to have the existence of a one-dimensional configuration is that between the two wells there is no zero in between. Okay, so W should stay strictly positive in here because anyway you know that all the transition will be done in here. And then okay, so then you can get even uniqueness up to translation, and that's the usual ODE. So you expect that this energy is, you have the equipartition. This is equal with this. You get to this ODE, and then in fact the so if you like more geometry, so the energy of the one-dimensional configuration is nothing but the length of your geodesic in this hyperplane with the metric W. Okay. So that's easy. But now when you go in higher dimension, so that's where you look the zeros of W. So you want to make the transition between U and U minus. Then, of course, you could have several geodesics appearing there. But the problem is that, for example, if you put another zero here, so of course, the geodesics will give you a distance. But the problem is that if the cost of this geodesic is the same like the sum of this and this, then this is typically where you have lack of compactness. Okay, so this is a condition that we need to put in there. So the existence of this. So as I said, we are interested what's happening in this plane. So when the first component is A. So we minimize the 1D transitions there. So of course this is an equality. So this that is bigger than that, you just do Cauchy-Schwarz. And on the other side, if you take a configuration like this, then if you change the parameterization, then you can get back here. Okay, so in order to have existence, what you need to assume is that in that hyperplane you have just a finite number of wells, that W cannot go to 0 at infinity, so there is no artificial 0 at infinity, and then you have this strict inequality so that you avoid this lack of compactness, and then you can prove that there exists minimizing transition. Of course, it's not unique because you could have several geodesics, and the energy is given by this one. Okay, but let's say that that's a 1D problem that's not so difficult. So now that's the main point that's the main point of my talk. So let's say that you can forget of what I said up to now and focus on this. Okay, so let me, so the aim was to characterize the potentials for which you can get the one-dimensional symmetry. So in dimension 2, if you think to the Aviles-Giga problem, then we can prove that for every potential that is the square of a solution of the wave equation or of a function that is harmonic, then the answer is yes. Okay, so in particular, so the Aviles-Giga is what? It's like 1 minus z1 square minus z2 square. So that's a solution to the wave equation, right? If you derivative twice, is the same like deriving twice in the x2. So that's okay. Then you could place here a solution, an harmonic function. It's okay also. And also you could go to that potential that appeared in the segregation phase model, and also there it works. So this is a condition that proves that every global minimizer is 1D. Of course, there is a condition here that you should ask that U stays in L infinity, because as I said, there is no maximal principle. So in the scalar thing, it's easy to say that, well, if at the boundary you are like this, then you should stay in between. For a vectorial, you cannot do this. But if you don't like this, then you could go and ask an additional condition on W that is this kind of exponential thing. So this is nothing but because in 2D, so this quantity controls this kind of exponential in U. So this is called the Moser-Schrödinger inequality. So, and you need it for some regularity reasons. Okay, so what's the, so I said that we will use this calibration method. So the calibration method is that you will replace your energy with a simpler energy that stays below your energy, but still it will match the upper bound coming from your symmetric solution. So what is that calibrated energy that you put here? So in general, you will put what is called a null Lagrangian density, which is a divergence form, that you will ask to be less than your energy density plus some term that is also in general null Lagrangian, but is divergence. It's integral zero. So when you integrate here, this goes away. So you will get that the energy is larger than this energy. So, of course, that's a boundary term, which is fixed, okay? So like this, for example, you get a lower bound very easy. But now the problem is, okay, here you ask this inequality for every admissible function. So then you say, okay, but I want to have an information point-wise, okay? In general, there is no recipe to cook up such entropies. Okay, but that's just the first step of your proof, because after it, what you need to do, as I said, you need to prove the matching of this artificial lower bound with the upper bound that comes from your special solution, which is in our case the 1D. So this is what is called that your map phi is calibrated after this solution, because you will ask that this is equality, right? So like this, you see directly that since for every configuration this is larger than this, that is this, that U star is a global minimizer. But now we want to prove more. We want to prove that every global minimizer is 1D. So that's the trick now that you will use. So if you will have another global minimizer, then you know that this is equality. So you will have that this is equality. And in fact, when you have equality there, your second order PD will in general be just one order PD. So it's much easier to solve. And let's do, right, I still have 5 minutes. Oh, yeah, okay, thanks. Yeah, but I'm almost done. So let me prove you, because that's easy, the Aviles-Giga question. So how you prove the symmetry of every global minimizer? So we said that the W is a square to a solution to the wave equation. So which is the case for the Mexican head potential. Then the ansatz, as I said, there is no recipe to cook it. But in this case, the recipe will be that to look at the calibration where the gradient is given by this alpha that is didn't appear up to now, and W that is here. Of course, when you want that this equation is fulfilled, that's a gradient. So this means, so in my notation, that this is the gradient of phi 1, and that's the gradient of phi 2. But of course, in order to be a gradient, then you need to have that Schwarz lemma, right? When the derivative in the second variation of the variable of this, it's equal with the derivative of this. So, but this is exactly equivalent by asking that this is wave equation. So that's why we stick to wave, okay? If you go with the harmonic, what you do is that you put a minus there. And if you like complex analysis, you see directly that that's nothing but the Cauchy-Riemann system. Okay, so that exists for wave. And then what you want to see if this divergence is less than your energy density plus something, okay? So I go here with equality. Okay, I know people maybe are hungry, so I won't make you upset with this computation. So so this is negative, so that's good. And then you have this divergence coming out. Okay, so this is what we wanted, right? I mean, we wanted that this inequality is fulfilled for every u, that is divergence-free. And now the second one is to see if the saturation condition is fulfilled. So the saturation was nothing but this boundary condition. Of course, so since u plus and u minus are there, this is nothing but integrating phi 1 in the second derivative. But this is nothing but w, okay? So w is the square root of this, but that was exactly the geodesic. So you have it. Okay, and now I said, right, but this just shows that the 1D configuration is a global minimizer. But now you want to know if you have another global minimizer, can you prove that is 1D? And now you need that, so if you want that the energy of this is exactly this energy, this should be 0, this should be 0. But now if, for example, this is 0, since you are also divergence-free, this means that d1u1 is equal with d2u2. So already here you are done. u2 do not depend on the second variable, depends just on your variable. And then, okay, due to this condition, you also prove that u1 depends just in x1. It's easy, okay? But that was the 2D case. So what can you do something in higher dimension? And the answer is yes. So for example, is this nice example that we cooked up, that imagine that on your Rn space you prescribe n+1 wells. And you also prescribe a distance between these two wells. Can you prove that there exists a potential that will have these prescribed wells with the geodesic cost that is exactly your prescribed metric, such that every transition is 1D? And the answer is yes. So that's the theorem. And here the trick is that okay, the entropies will be given by this kind of Lipschitz function that you should cook up after your prescribed metric. And it's something that, so the entropy depends on just one variable. And then, of course, the natural question is, what's the equivalent of the Aviles-Giga? Yes, this is my last slide. What's the equivalent of the Aviles-Giga potentially in dimension 3? So would be just this, but in fact, you need to put some penalization here, which says that it's not the full ball, the zeros. Of course, that would be not possible because then you would create a curve of zeros in this plane, and then you know that the minimizer cannot exist. So you still have in the plane the S1, but then you have also two other zeros appearing here. So also in this situation, you can prove that the 1D is the unique minimizer. Thank you.
Questions?
Yes.
So the condition that you were referring to is sound like some kind of strict convexity.
Okay. I don't see. So there is a relation, for example, with the calibrations. So you know that when you can cook up a calibration, you can suppress so the equality. This is something. But so of course now I know that there is also some relation sometimes between the convexity of the problem and the existence of calibrations. I mean, of course, the model was not convex, but like this. So you should tell me what do you mean by convexity. But yeah.
You had these conditions in your theorem. You had these conditions for when your method works.
Yes.
Do you know if they are sharp?
Oh, that's a very good question. Okay. In fact, so you mean, can you have some other equation here? Very good question. So in fact, you can, okay, you have, right, this is the condition, W11 plus minus W22W is 0. In fact, you can also put here minus a function that depends on Z1 and impose that F is less than 1. So this is called in physics the trichomy equation, which is so this is like going from a supersonic regime, so where you elliptic, and subsonic where you are hyperbolic. And so within this condition it works. And now if you, I said that, well, this Gin and Cohn said that when you put this, it will not work when delta is small. But what is the delta here? The delta is like 1 over delta here. So see that, of course, there is a coherence within our result and that, because this is much larger than 1. Okay? But of course, I don't know the full set. But I know that there is, I mean, it's not just wave and harmonic, there is a link. But I don't know what's happening outside. Yeah, that's a good question.
Let's have our next speaker set up, and we can take one more question in the meantime. There's a quick one.
Yeah, that's a Blackboard talk, so that's.
Oh, okay. No setup needed. So
that's pure, yeah.
All right. Well, let's thank the speaker again.
Thanks.